It is my great pleasure to introduce Professor Krishna Biswas, who is with us at the Department of Material Science and Engineering. Professor Biswas is an expert, as you can see, in microscopy as well as in solidification, physical metallurgy as well as nanomaterials. So there are quite a few participants who had some queries regarding solidification and some nanomaterials. So I will request that please interact with Biswas sir, and without wasting any more time, I will request Professor Biswas to go ahead with the talk.
Yeah. Okay, thank you, Nilesh. So I'll just take about 1.5 hours maximum to tell you some important aspects of scanning electron microscopy. And as you know, SEM is a routine things for material science engineering students and also faculty members. But we have got large number of facilities in India now in many institutes. The problem is how to use those facilities. So as I saw, this is the SEM we have, the latest one in our department. Is there on our home page also, Nova NanoSem. Okay, so electron microscopy is do with electrons. We use electron, nothing else, as a source. And we can image in many ways. So as you know, you have already given a lot of lectures on structure, right? We know the structure determines properties. And I said we means it has already been discussed about X-ray diffraction and many other things about structure of materials in this course already, yesterday also, today also. But you know, structure has different levels. One is the structure by X-ray diffraction, which gives you crystal structure information. Other one is the microstructure. And it is important to know that the microstructure also affects properties. So one is this crystal structure which affects properties. Other one is this distribution of different things in the material. Simple give example, all of you should know this. The grey cast iron is used in where? Any idea? Where you use grey cast iron?
Machine beds.
Yes, machine beds, engine blocks. All the engine blocks are made of grey cast iron. But it is brittle. It consists of graphite and you see also iron. Iron means maybe perlite or maybe ferrite. Okay. But it is brittle, rather brittle, not very brittle. Correct. But if I change the graphite to this, is ductile. Phases are same. You will not get difference in X-ray diffraction pattern, but you change the structure. This is typical optical micrograph we get. So this is what you need to understand, the connection between these structures with the properties. I hope at the end of the lecture I will be able to do that. If I am not, then excuse me. Well, there are many others. This is one, another example, cemented carbide tools. These are all tungsten carbides and it is in a matrix of cobalt. Typical tungsten carbide tool tips used in the machining industry, a very large, big industry, about $300 million in the world. So these cemented carbides are basically very hard, very difficult to sinter. But distribution of these carbides, particle in the matrix determines its ability to cut. So we have to control that. This very important microstructure, ferroelectric domains in barium titanate. I don't know whether can you see the domains here. This is at a very fine level, not like earlier ones. Earlier pictures were from optical micrograph, but this is from transmission electron micrograph. So you can see here details inside the domains. Okay, so therefore these structure inside these grains play a very important role. Now we have many other things, color pictures, right? That's just become. So we also do, see, look at this sentence, microstructure can be art. These are all art forms. And these are not generated by us, generated by the material. It has been, these are not artificially made. This is done in SEM, where I think Professor Gurda will give a lecture tomorrow, like on EBSD. EBSD. So I will not talk about much on that. This is a modified picture, a modified metallograph using color etchant. This is again some phone call? No. This is again EBSD my IPM map. So you can generate all kinds of microstructures. But why do you do that? To get information out of it. That's more important. What we normally make mistake in the real life is that we can look at it, but we don't understand it. What is the inside? What information it carries? And at the end of the course, you must have that idea. So that you go back to your colleges, obtain a microstructure like this, but you will be able to read it, get information out of it. And that is where the most of the people lack in understanding. Okay. So I have given you ideas. Now scanning electron microscope everybody knows, I have shown the picture. First thing it gives, it uses tiny electron beams to scan of the surface. It's just like a television. Television also capture images using a camera, CCD camera. Camera is a charge coupled device, and then based on the intensity of the light, you capture image. Like my hairs are black, so very little radiation goes to the camera, but this has different color, so it gives you different kind of information from the skin, and then you project it on a TV screen using a picture tube. Scanning electron microscope behaves almost similar to that. You bombard the material with electrons, collect the signal out of the material which comes out from the material, and then you project onto a screen, computer screen instead of a TV screen. This is what exactly it does. Okay. But the important thing lies what all information it comes, what all interaction happens with the material with the electron. That is where the information lies. So mostly the signal output is always synchronized on a play. I don't know whether something is coming from the display, that's why these things are a little bit apparent. I hope you are able to read. And you have backscatter or secondary electrons. Backscatter means what? I throw a ball onto the wall, it comes back in the opposite direction at a 180 degree angle. It's called backscatter. Secondary means generated from inside by the electrons in the material. They are called secondary. We will show pictures to you to make you understand. Okay, and this is what it is. So you have a very small machine, very small machine. You see here, 2 computer screens which display these images and other things, and you have detectors like EBSD or detectors like EDS, energy dispersive spectroscopy, or any other detectors you can put it here. There are many things you can put in the machine, and it's now a very small tabletop instrument where anybody can use, even child can use, and you get this information. Okay. Out of this, it looks like a pattern structure, but this is not so important microstructure which you will see. What it can does, it can magnify to high level. This is wrong actually, it can go up to 10 lakh times nowadays. 5 lakhs is very easy, and it can have a resolution. You can see here, these are the final data. You can go down to 50 Armstrong, means 5 nanometers. Even lower actually, people say you can go up to 1 nanometer. The most important thing which this picture shows is this excellent depth of focus, which you cannot beat with any other techniques. Excellent means depth of focus means you can focus both things which are at the bottom at the top of the valley same time, and very easy sample preparation technique. Anybody can prepare samples, right? Even the college school students nowadays sometimes they come not to us, other places I have heard, can you see my sample, what is there inside? So you don't need any sample preparation much. That is another advantage. So what does it has? This machine which I showed you. Okay, basically it has electron gun. It has to produce electron. We don't use X-rays like X-ray diffraction. We use electrons directly. In X-rays also you use electrons, right? X-ray tube is basically you hit electrons on a particular metal and create X-ray. But here we don't do that. We rather use the X-rays to analyze the material. So electron gun is very important. We'll spend time on that. And this is a typical formulae which you need to know. I don't know how many of you have seen this one. This is very easy. This is whose law? Who has developed, got Nobel Prize for this? So lambda is nothing but hc by E. where h is the Planck's constant, c is the velocity of light, and e is the voltage. Okay. So this is de Broglie's formula, right? Now you can actually get lambda using non-relativistic corrections, where your velocity is not corrected by relativity, like because velocity of light is velocity of these electrons can be very high. In that case you have to use this term, extra term, okay, q square v square by c square. This comes from Einstein's relativity formula, and any textbook will have that. But in scanning electron microscope, because accelerating voltage is very low, so you can use h by m0 qv actually. This formula can be easily used, because this is the p actually. P is the momentum. E, this is not E, this P momentum. So momentum comes because of mass into velocity and q. Anyway, and you can have, I think here you can see clearly probably. You can convert in terms of volts, other things. But fact is that the wavelength is very small in scanning electron microscopes, because you have very large accelerating voltage of the order of 20 to 40 kilovolts. So because of that, lambda is of the order of actually Armstrong, or you can say it's very small, Armstrong level. So you can actually have, you can see you can have a resolution of very high level here. That's the biggest advantage. So these are the values of lambda. At 10 kilovolts it's about 0.12 Armstrong. If you consider relativistic correction, 100 kilovolts it's even less than Armstrong. And this actually opens up a question that why don't you see atom if it's so small? That's a separate topics that has to be dealt, because we have problems in our lenses when we view something and we cannot get the exact information back. Okay, giving this information, this is what is scanning electron microscopy is. You have a gun which generates electrons. This is the objective lens which focuses the electrons to the sample. It's completely different from any other machine. And then you have all these detectors which amplify the signals and display on a CRT screen. It's not CRT anymore, it's a computer. Okay, these are all, you can say, LCD monitors. And you have a scanning coils. This is scanning coils which scan the beam. You can just like you move the beam, you apply the voltage into it, so they scan. This is called scan generator. That's it. This is the simplest possible machine. In fact, this machine is same as what optical microscope has prepared by Leeuwenhoek long back, 1625 or something like. So he has also used a source of light, then lens, and then focus it. Here we don't focus, we use signals from the sample. So this boils down to that, what are we can generate signals from a sample. That's very important, which I will come to a very sometime later, but I am just giving you an introduction to the machine itself at the beginning. Okay. So that's it. Now electron gun, for you to make you understand, electron gun is just like a tungsten filament for most of the machines, and so you pass current to the filament, then it emits electron because of thermionic emission, and then this can be focused by a set of lenses. This is the Wellnut git which allows you to condense it. Then you have a condenser to form a beam, because this will scatter, electrons will come from all sides, so it will scatter. So you have to condense it, focus it to get an idea. This is the simplest possible thing people use, but nowadays we have gone ahead. Okay. So we can actually make the electron tunnel through, right? You can make the electron tunnel through a barrier. This is by quantum mechanical definition. As a person, he is a barrier, he doesn't know how to go here. So you can make it a transparent and he will tunnel through. How does it do? Okay. So this is the way it is done. Don't look at read this, just follow this. If you have a source which contains electrons and then you apply a voltage, okay, what will happen? If you apply huge voltage between this sample and the lens, then the electron, according to by quantum mechanical definition, electron will just tunnel. Tunnel means it will simply run through. If you do that, you can create a very, very high sources of electron. In tungsten filaments, what happens? You are heating it up and you cannot heat it uniformly, the filament. So because of that, the electron which comes out will have different energies, correct? And because of the spread of the wavelength of electrons will be large. And as you know, as the electron wavelength spread is large, you have more aberrations because of the lenses. It's very simple. chromatic aberrations from the light is same as this one, because light has different wavelengths starting from red to green. So, because of that you have the aberrations in the lens. Same thing happen will in the tungsten filament, but here because electrons are tunneling through a barrier and you are applying a huge field, because of that the energy width of the electrons coming out will be very small. That is the one thing. Second thing is that depending on your source and the voltage, you can drag more electron. You can actually have a larger number of electron per unit area. With tungsten you cannot do that. You can keep on heating it up, but after some time it will melt. The problem with tungsten is that. So there are the two basic advantages. That's why all these electron SEM nowadays comes with a field emission gun. These are called field emission gun sources. It has many advantages. First advantage is that wavelength is not changing, but your aberrations are reducing, okay, so that you can reduce the width of the electron energy by using this tunneling aspect. Second is that your source is more brighter. Brighter means, bright means what? If your number of electrons per unit area is larger, then it is more brighter. Sun is brighter than moon or maybe stars, because sun is giving more light, is radiating more light. Same thing, exactly same thing happens. So this is the source which is used widely in the see, you can see the voltage to be applied is field to be applied is 10 to the 7 volts per centimeter. If you want to use a cold means you don't heat it up. Heating is very small here. Even if you are heating it, it's very small, of the order of 40 to 50 degrees Celsius temperature. But nowadays all SEMs, even our SEMs has, you will see they have a cold fag. Okay, we don't heat these things at all. We simply drag the electron out. But question is that you have to pay money. Each of these gun cost about 1 crore. Okay, it's very expensive. Why? Two reasons. One is that this is a crystal. This is a fine crystal of tungsten. It is made in such a way the tip of this crystal is along a certain crystallographic direction. Okay, what is that? Tip of this crystal is along 1O direction of tungsten. Why it is along 1O direction tungsten? Read it. The work function of tungsten or of any element depends on crystallographic directions, because electron availability varies on that. So this making this crystal is expensive. Second thing is that you have to keep this whole thing in a very high vacuum system, 10 to the minus 7 to the minus 8 torr. So that requires extra pumping. That's why the gun assembly is very expensive for these machines, but it gives you a lot of extra advantage. So I thought I should tell you, because this is something which you don't know. So that's what is written. Cold tip is means smaller delta E, and it improves coherence. Coherence means that laser is a coherent beam. Why? You know why laser is called a coherent beam? This is a coherent beam because the beam moves from here to there. The spread is very small. Same thing. More cost, fussy, all kinds of problems exist, but it is the rule of the day. Lens works on this principle. Everybody should know that. What is this principle? The force is charge and the field. Okay, and yeah, this is same as optical lenses. Optical lens also, but we have a Lorentz force acting on that. So using this Lorentz force, you can move the electron, you can focus the electrons, you can scan the electrons, all the things. But what is the problem with these lenses compared to optical lenses? You need to cool it with water, because this generates a lot of heat. In optical lenses, like this is an optical lens, right? There is nothing like a heat generation. Here you need to cool it down. So that means the efficiency of the lens depends on the cooling efficiency. Okay, but advantage is that you can change the lens power by applying more and more different kind of currents. Okay, you can apply different charge and then you can change it basically. That's the advantage. Same lens can be used for different purposes. So lens are link separate. Let me show the picture. I hope it's there. Yeah, this is a sample geometry, not a lens. Somewhere it should be there. Okay, if it's there, I'll show you. And they are actually generate magnetic fields. Electron pass through the hollow center. It can focus it, and you can control using aperture. This is a sample setup nowadays, which they will show you. You can have a carousel. You can put many samples in one thing and place the sample inside. But remember, this is the wrong way. That's what I am showing the picture. You never put a bare hand inside a sample chamber. This is wrong, because if you want to analyze the sample for its purity, for its compositional analysis, you should not use a bare hand. Hand has a lot of dirty things. Okay. Not only we touch different things in the day, also it has secretions from the body. So that's the wrong stuff. Samples can be conducting or non-conducting. Okay. So conducting requires no preparation, or non-conducting requires you have to use either gold coating or silver. It's a simple silver paint, very cheap, or you can use carbon also. People nowadays use chromium. As I have seen somewhere, people use chromium coating, but it's not a gold coating. Okay, it's a gold palladium alloy. So you should use a very expensive one. So because it forms a continuous layer on the surface. Okay, now let us compare. You have seen this, right? So the first probe. In fact, few days back I was reading a literature. Even light will be used to probe our human body tissues. First probe people use is a light, which is abundantly available. That's why optical microscope came. Then came the X-rays. When the X-rays came, 1911, right? And you know how many Nobel Prizes are given for X-ray diffraction? Only one. That is Braggs and Braggs. Then Van Lau, Madame Curie, so many people are there. Okay. So X-ray can be used for diffraction, spectroscopy, and these normally, I don't know how many of you have been exposed to the neutron diffraction and SEMs and other things. You can use neutrons and ions also. On the other hand, electrons, it has large number of applications. You can't imagine how many. I think I have listed only few, but many applications are there. Correct. So what it says is that what all you can do with so many sources, with one source you can do everything. That is the biggest advantage of using electrons. Not only that, you know, electrons can be easily focused compared to other things. Okay, other things like neutron and ions very difficult to focus. X-ray is also not easy. So electrons can be easily focused. Okay, you can do holography, you can do diffraction, you can do spectroscopy, you can do imaging, all kinds of stuff. Okay, Lord, let me just, this is another microscope of same caliber using geol. We have a geol microscope here in HCMS. I don't know what is this. What is that?
7100.
7100. Even better than these. Okay, 6700 F. F stands for analytical capability. This picture is a famous one. Everybody shows in the lecture. This is what? Human skull. Yes, these are the eyes of spider. Have you ever seen inside it? How many eyes they have? Yes. So this is what is the first time when you go to this SEM, this is the first sample your instructor will show you. Okay, very easy to see, very easy to focus. Sometimes they show some insect, other insect also. Yeah, now comes the real aspects of that. You know, this is very important. Why? Because we are probing with electrons. So you bombard electrons, electron will go inside the material and it will create an interaction volume. How is the big is the interaction volume? That will tell you from where you are getting the data, information. And this is something students do mistake always. Nowadays you can do imaging using cold fake guns by a voltage of 0.1 kV. How many of you tried? 0.1 kV, 100 volts. You can start with imaging. We have lenses inside this column with which you can do that. It's called through lens imaging. So from 0.5 kV to 30 kV, 40 kV is the range of voltage people use. Remember one point. Here the interaction volume is very small, 35 angstrom depth, and here is 3.1 angstrom. Almost how many times can you calculate? Anyone in the class?
60 times.
Only 60. 1 micron is 1000 angstrom. 3.1 is 3100 angstrom. Divided by 35? 1000 times. So you got a message. If I want a thin film to be analyzed, I should use a lower voltage. If I want a bulk sample to analyze, I should use a larger voltage. This is done long back by these two guys. Never heard of them. Okay, Okayama and Kanaya. They are given a formula. Depth depends on atomic weight of the material other than beam energy and density. This is what we don't take into consideration. Okay, this is 1.67, this is 0.89. Simply you can calculate using this. These are all MD simulations done in a computer. Okay, these images you see. This is basically it matches with the prediction of this formula. Second important thing is this is the depth. What about the x and y dimensions? That's quite large. Okay, you can see here. That's quite large. So therefore, sometimes you get spurious elements, in your EDX pattern or something. It's because you have used a wrong voltage. Please remember this aspect when you're sitting. That's why when one of my teachers used to tell that doing electron microscopy means sitting in a cold, dark room, using your hot brain to think. That is the biggest challenge our students always face. Sitting in a microscope, in front of a microscope, they stop their brain working. Then they collect the data and they come back, something wrong happens. So these are the things you should not forget. Okay, this is something wrong, no need. These are all history of electron microscope. Okay. This is same thing. Okay. Yeah, history is very important. This is about the TM. Sometime it will be there. Okay, forget it. Fine. Difference between, I told you depth of field, and I want to show you again and convince you that you can have, this is the optical micrograph, and this is the scanning electron micrograph of this titanate. You can even see the growth step of the crystals, which is not visible here, because of very high depth of field or depth of focus. Okay, very, very large. You can see here, this is sitting at the top of the hill. The distance from here to there will be about 30 micron. But you can focus it all the down using different kinds of what's called different kinds of detectors, which is not possible in optical microscope. So sometime, although this is not true here, sometimes people say in an optical microscope you get a two-dimensional image, in ACM you can get a 3D image. You don't get a 3D image at all, but you can generate the 3D image using these 2D sections. This is one biggest advantage. Okay, so what all you do in a nutshell in ACM? You do all this stuff nowadays, but these are not all. Many things else you can do also. First is most routine thing you do is a topography. How does the surface looks like? Okay, those of you who have broken samples, fractured and seen under microscope ACM, this is what you should look at it, right? How the surface looks like, whether there is a brittle fracture, ductile fracture, mixed mode fracture, intergranular fracture, or intragranular fracture, all these things can be obtained from this. And ACM is the best tool in this world. No optical microscope, no transverse electron microscope, no AFM. ACM is the tool. Please remember this. Second is the morphology of phases. This is what physical metallurgists like us do. We prepare a sample, we want to see what is there inside. Okay? We have not broken the sample. We simply pick a sample and see. Then third one is the composition of different phases. You can either use EDS or WDS depending on the money you have. And then the last one, which Professor Nilesh Gura and Professor Sangsakar does a lot, is what is known as crystallographic information, which was not possible in before 1990s. So the theory was available, but the thing came out when the machine was made and the softwares are available. So you can actually have a crystallographic information from each grain of the sample. This is possible now, and you can do much better. Okay, so that's what I said just now. This is the simplest thing you do. Okay, tell me one thing. Oh, it's written there. These are the mistake I have done, right? This is what kind of fracture? It is the crack is passing to the grain boundaries. So grain boundaries are weaker than the grains, right? One example where it can see this, where the grain boundaries are weaker than the grains.
Sensitized stainless steel.
Yes, very, very classic example. Sensitized stainless steels. Stainless steels will have this chromium, right? It creates problem, chromium carbides. So by looking at this morphology, you can clearly say that. You don't have to ask anybody else. On the other hand, this is a picture of intragranular fracture. Okay, intragranular means within the grains, the cracks are passed to. from one grain to other, or like through the grain actually. That can happen if the grain is brittle or more brittle or has ability to fracture easily more than the grain boundaries, correct? You can see here the two pictures are given. This is again from barium titanate samples, some source. So you can easily do this in a SEM. You try. In fact, this is something which you should use if you are teaching SEM to somebody.
Sir,
Yeah.
sir, shall we say ki it's melted?
Pardon?
Melt. Is
No, this is not melted. This is, you can see here, this is, I don't know, can I say something? I don't know, maybe Nilesh is better. You have seen river patterns or cleavage type fractures, okay? So this looks like that. There are pores, these are pores. You can see here, these are actually pores. And the crack has gone through one grain to other grain. Otherwise, it could have been looked like this. Now, I don't know whether shall I need to talk about this. This I have already told you, right? Different scales which you can analyze from X-ray to the component. It goes through this microstructure. Fine, this is not required. Yeah, this is very important slide. I thought I'll tell you before, but this it tells you what all you can do in an electron microscope. If you have strike material with electron beam, it generates at least 10 different types of informations or signals. The first one it generates is secondary electrons. What are they? Simple. I bombard electron with the material, it interacts with the electron in the material, or rather it ejects out the electron in the material, and they come out with a much lower energy from the incident compared to the incident beam energy is called secondary electrons. They are very easy and to generate and abundantly available, but remember they come from a very small depth, because if they come from larger depth, energy is low, they will not be able to come out from a sample. And then you have a backscatter electron, which is just, you know, the electron falls on a nucleus, but these are not true anymore, okay? Quantum mechanics has changed everything, but you can use these things for the students to analyze. If the electron hits directly the nucleus, it will go back. That's called backscatter, but this is not true. It happens a different way, which I can tell you in a detailed manner later, but normally we say that. Now then you can have something which passes through the sample is thin. These are all called elastic scatter electrons, inelastic scatter electron, they are all transmitted. And you also have something known as non-scattered, unscattered, who have not undergone any scattering. Scattering means what? Anyway, by the way, scattering is a word which is used frequently. Scattering means what? The way I used to read when I was a student in college days, light goes a straight line path. The moment light bends and reaches somewhere else, we call scattering. Same thing here. This is unscattered, means it has gone without changing its path directly. These are scattered. So we are not using these things in SEM. Now it also generates X-rays and auger electrons, right? Why X-rays? Because if the electron, incident electron, eject out an inner cell electron, it will go out, it will become a part of secondary electron, but there will be a hole created in that inner cell, and that is an unstable structure. So outer cell electron will jump into the inner cell electron, and this process will lead to energy loss, or rather emission of X-rays. And auger electron is a 3 electron process. The moment the electron from outer cell jumps to the inner cell, it leaves energy. That energy can eject another electron from outer cell. That is called auger electrons. These are the subtle differences between these two. So this is a 3 electron process, this is a 2 electron process. You have to understand that. And we can use both of them. But remember, because auger electrons are very low energy electron, they only come from the samples, very thin layers of surface. So thin films analyzed can be analyzed, not by thicker samples. Correct? So I can broadly categorize 2 categories, which is electron signal and photon signal. Okay, another thing, cathodoluminescence, I didn't talk about it. It can generate light also. Okay. Any of our machines, I am not sure, in our institute has this facility of cathodoluminescence. Do you have it, Nilesh? No. No machines. Electrical engineers requires that. Electronic engineers requires that. They have fibers, bombard the electron, it will generate light, and they should be able to detect that light. But we don't have. There are discussions to have it. So for the material scientists, normally we don't use cathodoluminescence, but we normally use other things. So you have all these interactions. It is you how to detect them and use them. That is the things the SEM does for you. correct. So please remember that. I leave behind all these slides. This is there in SEM big books, and I'll skip these things because there are so many things to be there, but something, okay, yeah. Now, yes, I told you that the electron wavelength is very small, of the order of Armstrong and less than, right? But we never get, you never get the resolution which is required given by the electron beam size, correct? You know the formula of Abbe's formula of resolution? Nobody. If I have a source, light source, electron source, 0.61 lambda by numerical aperture. Numerical is mu sin theta. Mu is the, and what is sin theta? Theta. Yeah, something like collection angle, not exactly collection angle. The lens collection angle is known as theta. Okay. So you can change the mu by replacing, optical microscope people by replacing the column using a vial instead of air. Air has a very higher value of lower value of mu. So if you use higher mu, resolution will improve. But you can't change 0.61 lambda. That's a fixed. And I want you to go back where from the 0.61 lambda comes. Pardon? Rayleigh's criteria, yes. You have an object here, you want to see an object there. So how will you see? You have two light sources, there are thousands of light sources on this, okay, because this is a very blunt object. Each of them should be separately seen on the image plane, right? So there is overlap. From there it comes. That's the Rayleigh's criteria. So now question is this. That's fine. We can change, mu. You can change lambda using different sources. But what you cannot change is this. Okay, this is the, you see, the way to improve resolution is by reducing the size of electron beam. Electron beam size, the resolution also depend on this factor. This is known as aberration constant. Any lens, whether my lens or your lens or whatever, electron lens undergoes aberrations. And there are two types of aberrations. What is the first one? Spherical aberrations. What is spherical aberration? You have a single wavelength. If it goes through the center of the lens and if it goes to the periphery of the lens, you cannot focus both of the beam in the same position on the image plane. You know that, right? That's not possible. So a point will be seen as an extended object. And you cannot prepare a lens, although it has been done, but I will not talk about it. You cannot prepare a lens in which CS is almost 0, correct? Because it is the manufacturing fault of the lens. In optical lens, you can have convergent divergent type lens. In the camera, it is there to reduce this spherical aberration, but you cannot make it 0. That is the idea. Electron lens, you can't even go that. There are limits. There are other ways of do that. Now technology has come last 10-15 years. So you can see this is a factor of 0.25, the minimum size, and then you have a lambda to the power 3/4, 0.75, and these are all your current and other things, current and temperature. This is the current density of the source. This 3/8, very very funny formula. I don't know how these factors comes, but it's there in the books. You can read it. So fact is that if you continue reducing even lambda from optical to the electron, you will not be getting very low value of D, because this will be the deciding factor. So basically for the last 15 years, lot of research has gone into how to reduce this C phase value. Very small value, whether can I make it 10 to the minus 3, 10 to the minus 4, 10 to the minus 6. Lot of research has gone. And probably you will say the person who has changed this will get Nobel Prize in the 10 years time. His name is, I forgot his exact name, Helmut something. He is from Germany. He has developed a lens which is fitted with all the Titan microscope now, whereas aberration is corrected, aberration is completely corrected, correct. But for low current, you can simply, high voltage current will be very low, so you can formula. This is what you have seen in many books. Cs to the power 1/4 and lambda to the power 3/4. Okay. So these are all important aspects for you guys. Very very simple message. You can improve resolution by increasing the strength of the condenser lens. How do you do that? That means you can make the beam finer and finer and finer, correct? You can do by changing aperture, condenser aperture. None of you have tried, right? Our our teachers, I remember in ISC we have to change the aperture, condenser aperture manually. Nowadays you don't need to do that. You can click button, it will change. So decrease this beam size will improve the resolution. Decrease the size of the objective aperture, because objective beam, objective lens below there is aperture. There are aperture in the condenser lens, aperture in the objective lens. This is the most important one. You can decrease the distance, working distance between the sample and the objective lens. That is called working distance. If you decrease it, your resolution will improve. Please try that. Okay. Before trying these two, you can try this. You will see the change in the image quality. Okay. Few things about sample preparation. Most of you know about it, but if you have samples which are non-conducting, it can lead to charging, like ceramic samples or polymeric samples, right? And we coat it with carbon, chromium and gold platinum alloy. You can use carbon tape, most of you do it, carbon paint, silver paste, all kinds of things. What does it do? Why does it charge? If the electrons are not finding easy paths to go out from the sample, they will be collected on the top of the sample, and this will deflect these secondary electrons. Not only that, it will also increase the emission of secondary electron from the cracks or from the regions which are like hills or valley or the depths. Because of that, you will see periodic burst, and then you will see the sample will be completely white. You don't see any image. Correct. So these are all the coatings done on the sample. You can see here that these are coated, okay, using a machine, and then you can clearly see the image. The difference between this and this is there. Here you don't see the things there. What is inside this white layer? But here you can see clearly. Even the grains can be seen.
How this is sputtering?
This is a sputter coater. Sputtering is nothing but you have a gold palladium source and you have argon ions. You have seen, no, they put argon gas inside it, and if you apply a large voltage, not large, 3 to 4 kilovolts, so argon ions will be energized, and then they will hit this source on which you want to deposit thin films. So by sputtering, simply by sputtering, which is physical vapor deposition process. This is sputter the gold palladium.
You need to generate vacuum?
Yeah, you need to generate vacuum, but not high. A rotary pump can do that. These machines comes with all the ACMs nowadays, almost all. Even if you don't have, you can buy silver paste, is available in the market, and apply the paste on the surface. Advantage with this is that you can generate nanometer thick coatings, but applying paste you cannot do that, it will be thicker, then you will lose some information out of that. People even use, I know I have seen, you can buy graphite powder and dissolve it in some solution like alcohol and paint it. Okay, polymer people now even it is done. Okay, but this is a more better technique where you can control. Even nowadays you can coat with carbon. Carbon can be used as a coating material instead of gold, because carbon is very cheap. This is the difference you can see here, coated and uncoated. Okay, uncoated and coated. So you can see the difference. The pictures are reversed here. Correct. So this is easy, and yeah, okay, these are all silicon. Okay, now yeah, let me show the few images. This is secondary electron images, all this differently magnified of this silica spheres from a company called Heresias. 5 micron, 0.5 micron. You can see that you can, if it is coated nicely, silica is it's not a conducting material. You have to coat it with something, so you can magnify to a very high level, something like I think 10,000 times from there to here. And secondly, yes. Secondly, this is also important here. This is different levels of coating. Okay. Sometimes your sample will look like this also, image. Why? Because it has scanned but this area could not be properly scanned because of the charging problem. This is actually a picture, backscattered image. You can see different phases here, black and grey, so white and grey and black are present. Here you don't see anything, here something is there but not clear. So you can, by different coatings, this is very large amount of coating layers. As you asked, no, this is very large, this is small, and this is the optimum coating actually. That's why it is called native either. This is optimum coated sample.
Paint has
Paint will not allow you to see what is inside. You can see, you will not get to see exactly the sample surface.
Coating material structures will also come there?
Yeah, that's what I am giving. This example is that. Coating material structure will come. Here this is the situation. I don't know what is PPA. It's some polymer, carbon related stuff which has been coated on the surface.
So in the previous image,
This one.
we have these white.
These are again because of charging only, not fully gone. Okay. And same thing here also, magnified to different levels. Again, okay, let me just, these are all from different pictures, space tiles. Okay, now yes. Okay, so I have just briefly given you idea. Now let me come to the important topics on chemical analysis with SEM. You can do qualitative, quantitative, and also mapping. All the three things can be possible. So what actually it does? This is the actual electron path. If you have a bombarded electron, it will take a path like this, and a basket electron goes. It's not exactly like from the point of impact. And these are the secondary electrons generated. And you can also have X-rays, cathodoluminescence. This is taken from that master book of SEM. Edited by 7 members, there in our library also. So you can see that even if your lambda is 1 nanometer, you can have, okay, this is the depth, okay, that's what is shown. So depth for me, the secondary electron can come out is 5 lambda. This is 5 nanometer, not much. But depth from the backscatter electron coming out is almost 3 or 4 times higher than that. So X-rays can come out from this large dome, large area. So sometime you are under impression that I have bombarded an area with electron, I will get X-ray from that part. No, it comes from a large interaction volume. That's what you should keep in mind. So many times your computation analysis will give you wrong data because you have used the wrong voltage and excited large volume beneath the sample surface, and from where you are getting the data. That's what I want you to get. And this is shown here exactly. So you have electron beam, very small width, you can see here, but interaction volume is very large. So all your X-rays will come out from these. In fact, this is a very important picture. Secondary electrons comes from this part only, basket electron comes from this part, and this is it. So therefore, basket images which you see in real life, they are not only from the surface, this is quite deep from the surface. Sometimes your surface will not show many phases, but basket image will show many more than that, because things which are there beneath the surface will come on the image. And X-ray is coming for even larger volume area. So please remember these aspects when you are doing the actual microscopy lab. This is shamelessly stolen, this image, from North Arizona lab. I have done it. I have not given the reference. Okay. So I will not give you this picture. That's what I have written. Okay, X-ray I have told you how it is generated. I don't need to discuss again. So this is exactly is the difference between Auger and the X-rays. Correct? Can you see that? Do I need to explain? It's a 3 electron process. This is a 2 electron process. So you remove an electron from this inner shell in X-rays, and then an electron jumps from here to there. In the process, X-ray comes. But on the other hand, for Auger, what happens? It jumps from this to this, okay? Correct? And whatever is emitted, it removes another electron from the outer shell. It doesn't generate X-rays. This is not generated, but whatever is emitted this will remove another electron from the outer shell. That is called auxiliary electron. So it's a very low energy. So I know that every atom has a different definite structure or definite levels of the electron levels, energies are fixed. So simply by measuring this X-ray energy, I can know what is this electron, what is this element that is generating these X-rays. This is very routine stuff, right? Because I know that the difference between these and these energy levels. For suppose let us say magnesium, you specifically know that, and this is not same for magnesium, aluminum, magnesium, silicon, magnesium is others. So by knowing the energy, I can detect the characteristic energy, I can detect the elements. That's the most important thing we do normally. First thing you do is that I put the sample on the electron beam, and then you get all the spectrum, right? All the lines, the energy things, and then you can generate that. And this has already been taught. I don't need to teach, right? The difference between these and this, known, X-ray diffraction. Okay. Which one was discovered? Which one was first seen by Röntgen? Yes. How? You know a classic picture, his wife's ring. You have seen that? So that was taken by this beam, right? This is exactly a spectrum, and this is taken from aluminum. Aluminum will have oxygen, you cannot do anything about it. And this is the baseline, this is Memstelen, and this is aluminum, and this is oxygen peak, and they are K, because you can also get L for larger atomic number elements, not for others. Yes, now, this is also important, which is probably you have not seen this curve, right? See, we call the yield of X-rays like fluorescence yield, okay? Why? Okay, let me explain to you. We always tell our students that if you have a steel sample, don't do X-ray diffraction study with copper targets, right? Because it can fluoresce. What is the meaning of fluorescence? The X-ray which is coming from copper X-ray beam, what can I do? Is anybody in the class knows about it? It absorbs, right? Then what does it do? Deposits. Little bit think differently. Okay, let me tell you. How many of you seen the zinc sulfide screens? Have you seen on TEM the white screen, zinc sulfide? It's a fluorescent screen. What does it do? These are fluorescent lamps. How does it operate? No idea.
The UV light falls on the material that it emits.
Think about a tube light. You have gas inside it, 2 electrodes, right? So if you apply voltage, the gas gets ionized. So all these ions then fall onto a coated material on the surface of tube light. You break the tube light, you will find the white layer coating, right? When it falls on that, it generates light. That is called fluorescence. So for many of the X-rays, it gets generated, but it will not come out the same wavelength at which it is forming. It will interact with the other atoms, excite their X-rays, and a new X-ray beam will come. Same thing happens in stainless steel. A steel sample, if you put a copper X-rays, okay, it will excite the iron atom X-rays and come out as a source, right? Same thing happens. So fluorescent yield for the K cell elements is very large, very large. You can see it's almost 0.5. On the other hand, M cell is very low, L cell is very low. So therefore, if you use larger atomic number elements where M and L cells are, L peaks are present, what is the point I am trying to make is that aluminum you cannot get L excited or M excited these X-ray beams, correct? But you can get in platinum, you can get in bismuth, you can get in other elements which are heavy. They have large L electrons also, right? What is the difference between L and K? Here what an incident electron beam is has knocked out the K cell electron. So it can also knock out the L cell electron, but fact is that in aluminum it is very difficult because binding energy is a problem and it doesn't exist many of the elements also. That doesn't happen. So if you have an element in which L peak is coming or M peak is coming, it is better use those peaks to calculate your concentration of the element, not K peak, which you normally don't do in the experiments. See, if you go to a lab, SEM lab, they will use this peak because this is routine things, or this is a default. They will use this K peak intensity to calculate the amount of the material present, amount of aluminum present, right? But suppose I have an element which generates K peak, L peak and M peak. I should use M to get the actually best measured composition, not the K or L peaks. This is because of this reason, exactly because of this. Fluorescent yield is the lowest here, correct? So please remember this. You can do that, and this is what it said. For Z equal 20, the yield is very low. For carbon, others is different. Anyway, so kinds of X-rays. You can have these or these, and I don't need to explain to you, right? You are going to show them the EPMA?
No.
Not? You have to tell them.
Yes, because no EPMA.
You are only showing XRD and SEM. Okay.
This is a course on diffraction.
Okay. So it says it's just like a solar cell. That's a real sentence, correct sentence. You know how solar cell works, right? Okay, you don't know, forget about it. So what do? You have a material with all kinds of elements, bombard with electrons, generate all kinds of X-rays. Then you have a gadget. It's nothing but a filter. It's an electronic gadget, nothing but a filter. You feed these X-rays to the machine or to that gadget, okay? And it has suppose 2000 energy levels. Total energy difference, energy things is this one, aluminum kahan gaya? Okay. This is from 0 to 6 or 0 to 20 kilo electron volts, okay? This is the energy width, range of energy in which you scan these things. So you divide this one by 22,000 small windows. So 20 divided by 2000 is what? Each one will be 20 kilo electron volt divided by 2000. Each one will be 0.1. 0.1 kilo electron volt is each energy window. That means you have filters which can accept from 0 to 0.1, then 0.1 to 0.2, 0.2 to 0.3, like that. It has, the filters are made like electronically. And that means what? Energy is dispersed. The electron, X-ray beams or X-rays generated are dispersed by energy wise from 0 to 20 kilo electron volts. That's why it's called energy dispersive spectroscopy. The problem here is that you have resolution is poor, because you can see, you can have a filter of 0.1 kilo electron volts or 0.01, 0.001, 0.0001. You can go down as low as possible. That will improve your resolution, but cost will be higher and higher and higher. Well, electronics does not come as a free of cheap of cost, right? It's not a cell phone or like that. So that's why the resolution of these EDS are poorer, not, and you cannot rely on the data too much because of many other issues. So this is one aspect. This I have already told, right? Okay. And on the other hand, this technique doesn't rely on this. This technique relies on X-ray diffraction. What is that? Yes. Let me explain you this. What happens? You generate, this technique relies on Bragg's law. You generate all kinds of X-rays by bombardment. Suppose your element contains 10 elements, your sample contains 10 elements, okay? Oxygen, carbon, aluminum, copper, nickel, barium, all kinds of titanium, and each will generate X-rays because of bombardment of electrons. Each one has characteristic wavelengths because of energy. Energies are fixed and related to wavelengths. So now I can have a crystal, lithium fluoride crystal or whatever crystal, orient in such a way only one wavelength of X-ray will undergo diffraction by Bragg's law. I can do that, is it not? So I orient the crystal in such a way, that's what done in EPM, electron microscope, that only one X-ray is able to diffract, and then I can detect its intensity one by one. That's why it's a time consuming step. very, very long time it takes. Lithium fluoride is a crystal which is used for that. There are 4 different types of crystal I think it's used. Yeah, I am not correct, but maybe more. So that is one thing. Now we have a standard. You can have a standard there. Suppose you have pure aluminum, nothing is there. So first you bombard electrons with on the pure aluminum, get the X-ray from it, then do this diffraction, Bragg's diffraction, measure its intensity, store in your computer. Then you go to the sample, measure the intensity coming from aluminum, and these two ratios will give you the aluminum concentration. Correct? That is the technique which is more widely accepted and better for quantification. Correct? You understand, no? But it comes with a cost. It's not a cheaper things. Very, very important fact is that. So we didn't have this machine earlier. Now we have got, but as your coordinator is saying, he will not show you this facility. It's there in the same place where they could
we'll show them the facility.
But you cannot. Yeah, it is not possible to show the operation. You can simply see the facility. Okay, it's there in many places. So important. Okay, shall I talk about it? This is basically energy collection efficiency in EDAX of different sorry, in WDS and different things actually, crystals. Let us keep it about it. Okay, yeah, this is I have already shown you, right? Again, I am just telling you that please don't be under impression that I am bombarding my wave here. I will only get information from the side of the beam. No, it's much larger. You can see here, depth area increases, and that will give you wrong informations. Why? Because you don't know what is beneath the surface. Same phase from which you are measuring the composition, it may not be extending in the z direction longer. So if you bombard with a high electron, information will come from the other phase which is there at the bottom. Correct? So this is why you need to be careful while doing the EDX analysis. This is the lab lecture. See. Anyway, I will not go into this. These are all software related things. So you can these are all you routinely do it. That's what I wanted to show you in our SEM. Is there you get a spectrum. You can actually do the quantification using histogram. Then you can do mapping. Mapping is nothing but you can select area, map the elements present there. That is routine things people do. I don't know whether I have any pictures. Okay, not that. These are all our SEM. I don't know. This one you will not show, right? You are going to show the geol SEM, not this one. This is quite far. Okay, let us not talk about it. Okay, this is what something. In EDS detectors, there is something known as dead time. Okay. Dead time really means dead time. Detector is dead, and this is very important. What is this? Well, these are electronics, right? You feed the X-ray, or you feed the X-rays onto these detectors. It takes time to analyze the data, because there is how the detectors works anyway. Any idea how the detector work? No idea. These are called SILI detectors, SILI. They are not SILLY. Okay. What is it? Silicon lithium detectors. See what happens if X-ray falls on a SILI detector. Lithium ion is a mobile ion. It moves because of energy transfer, and if it moves, it generates current. Then you can measure the current, and from there you can measure the intensity. You have not read Khaledi's book where about chapter on detectors. What are the first detector? X-ray detector. Gas filled. Yes. How does it work? Gas get ionized. Measure the current. Now we are doing a solid state, right? The same thing. So, but then what happens? SILI detectors, the motion of lithium ion is a temperature dependent. If you apply at room temperature, lithium ion will move. Even on batteries, this happens, right? So that's why you want to only see the movement of lithium ion because of these X-rays. You have to cool down to liquid nitrogen temperature. That's why all of these detectors used to be cooled. They have a Dewar flux in which detector is kept, right? But it creates problem, because you have a liquid nitrogen layer, dual flux, X-ray has to penetrate those the distance. Then you lose informations. So nowadays we have got liquid nitrogen free detectors where it is no longer silly technology, it's a different technology. So there you don't need that. So this time where if you are feeding information at a faster rate, detector cannot process. And that time any information going to the detector will be useless. So dead time, that's why it should not be more than 20% in the detectors when you are doing the experiment. This data is shown real time when you are doing that. Please remember this also. Yeah, this should be, they said between 20 to 40 times, 40%, but I will prescribe do not go beyond 20%. These are all the things I want to show. So now let us ask if there are any question or something. This one I kept because this is the software we are using in our labs. And I am not discussing EBSD because EBSD will be separately discussed, so I am not doing that. So you have any questions, anything? Yeah.
In case we have low amounts of maybe carbon or oxygen, so how reliable is the SEM data? The
EDX data. Yeah, carbon is reliable. Until actually you can go below carbon. Below that, it's not reliable.
Carbon, like if we have small quantities.
Still, it will detect and it will give informations. Well, one more thing I should tell you, the yield of X-ray depends on 3 factors, right? One is the atomic number, that's obvious. Why? More outer cell electrons, so they can jump. And second one is your absorption. All the X-rays will not come out. It can get absorbed. Third one is the fluorescence. So first 2 factors are predominantly present in all the samples. So there is a way actually, now it doesn't come. I remember older microscope, basically there's a program will run in the computer, in the microscopes, which will correct these gap corrections. But even if you do this in carbon and oxygen, you will not get good quantified data.
So can we rely on the data that they?
No. You have to go to WDS to rely on that data. Carbon is extremely difficult in any machine because carbon is obviously present in all samples. So whether it's basically coming from the sample or your spurious is very difficult. Oxygen is okay, still better. Oxygen, nitrogen, you can do that.
Even in EPMA they struggle. That's what
Yeah.
Carbon percentage is not reliable.
It's not because you don't know how pure is your sample, right? Yes. Any other questions? Yes.
So this in case of EDS, you told about K alpha lines. Means from the inertia the electron is knocked out.
Yeah.
So it has the electron, the incoming electron will knock out the inertia.
Yes. Then the outer cell electron will jump to the K cell. That's why you call K lines.
It may, for me I felt like why the electron cannot hit the nucleus.
Good questions. Yes, definitely good question. Yes, it can, but it will not. Why? Energetically more expensive.
Okay, what is the energy I need to hit the nucleus?
That can be calculated. It's there. People have done it. But electrons are intelligent like you. So they will not jump into nucleus. They know they will die. Okay, it's like jumping from the train, moving train. Exactly same thing. They will let us jump to cell. Okay, but the electrons do not jump to the cell. By the way, you know how does they to move? Any idea? These are all terms we use in the actual sense are incorrect. Electron never jump. How do electron move? And do you think really electron jumps directly from outer cell to K cell? No, it goes through process. Total energy loss is that much. So all these things you have to go to the spectroscopist persons in chemistry. They will know. They never jump like that. They will tell you these are all garbage you are talking about it. Okay, but it explained all our stuff. That's why we are happy.
All our or physicists?
Our means material scientists. I will not say physicists. All explains our stuff nicely. Like all the diffraction phenomena we describe is not the way it happens that way.
Is it not like the wave functions are traveling like?
Yeah, you have to bring in the quantum mechanical stuff here.
One more thing, sir.
Yeah.
It's a general thing, like in our microscopy, sir. When we have electrons, turning to its photon nature.
Yeah.
Photon which is turning to its electron nature. So photon which doesn't have the charge value, doesn't have the mass value. How now it's getting the mass and charge to turning the electrons?
Now comes the physics people question. Yes. Okay. That transition from chargeless to charge matter or other way, it's not very simple stuff. Okay. It's whatever I understand, and I am not an expert on that. It happens to emission of some particles, which we don't detect. Okay. Yeah. No, we don't detect, but people have detected. Nobel Prizes has been awarded. Okay. Because finally electron consisting of so many, this is not a fundamental particle anymore. It has, yeah. So those things, they can get removed from electrons and then become chargeless. Correct. There is a electron which is positively charged. I don't know his name. Positron. Yeah, same mass.
In the pair production it comes.
Yeah, same mass. But how does it happen? That means there is a fundamental particle which gives its charge negative and positive to the positon. Okay, but those are not really in the realms of material science. Those are in the particle phases. So
How the tunneling is happening, sir? How the
tunneling is just like you tunnel through. There's suppose there's a big tunnel. Okay, one entry, one exit. You run through the tunnel. You reach from one point to other. Same thing happens there.
studied a little bit there, sir.
Yeah.
In the superconductivity, sir, in Josephson effects, when
That-
two superconductors meet.
But that is different thing, sir. That is
There
not.
are also some tunnel currents starts.
But that is because of formation of the pair Cooper pairs. Here it doesn't form. Here one electron is tunneled through a barrier. It's nothing but there is a barrier, okay, and it just passes through the barrier. It is like that only. It's not a free movement.
The magnification you told is around 10.
5 lakhs. 5 lakhs you can go any machine.
So is it optical magnification or a digital magnification?
No, optical magnification. Digital magnification can be very high. Yes. Nowadays even good ACMs magnification can go up to 10 lakhs time. It's possible. But routinely you can go 2 lakhs very easily. Magnify.
And why we cannot see the atom?
Yes. You really do not see atoms. You cannot see atoms. Why? It's because of Heisenberg's principle. You can't see. The position and velocity are not, there is uncertainty, correct? What you see is a potential. Even AFM also, what you see is a potential. Every atom has a potential, okay? Or like electrons has a potential, like that you map. The AFM, the tip is getting moved up and down because of this potential, the interatomic potentials, okay? So that is what is getting mapped. And we see a sphere-like things, we say this is an atom. I don't have that picture here from platinum, people have done that. You can even see holes there, everything. But these are not actually atoms. So therefore, only probably we can see those. Even electron microscopy also you see the potential, you don't see the atoms.
And in case of EDS, can we detect the molecule?
Yes. You are meant to say composition of the molecule.
Yeah.
Yes, why not? You can detect the composition of molecule because if you have one sample with a particular chemistry present, you can detect the exact composition of that. Okay, single phase material suppose, you can do that. Suppose polyethylene is present, it will detect, it will tell you the composition of carbon, hydrogen and other things. Okay, so then you can detect what is the exact composition and then a formula can be obtained. It's possible. Yeah.
So, one more question.
Yeah.
Can we have it over coffee? Okay, so I think it was, let us thank Professor Krishna Viswas for a wonderful talk.